Okay, cool. So let's have a look at the network stack. This is how the network stack is. Let's say you can look at the network stack from a logical level as an abstraction over three different things. We have different options for subtask output types. There is pipeline bounded, there's pipeline unbounded, which is basically pipeline bounded is for batch processing. Then for stream processing, we have pipeline unbounded, and we also have blocking channels and non-blocking channels. Then there's a second dimension. We do have different scheduling types. So you can either schedule tasks all at once. This is what is done for streaming. Or you can schedule a new task whenever there's input for it, or whenever you have the complete output from the previous task. Those two are for batch processing, basically. And then we have different options of tuning the network stack for high throughput by using buffers between between any two task managers that communicate with each other, or to go for low latency by reducing this buffer timeout. I'll go into details a bit later. So our network stack abstracts over that logical connection. What we basically have is, like, assume that you have two subtasks on one task manager and two subtasks on another task manager. Then logically, there's a connection between each of the subtasks whenever you do something like a shuffle from a keybuy or a rebalance. This is a logical view. Down in the network stack, we don't have separate connections for each of those. Those will be just too many for bigger jobs. We do actually multiplex there. So this is how it is beneath on a physical level. So we do have the two subtasks like before and here as well. But if we communicate through a shuffle, any two task managers will use only one TCP connection for that connection between the two operators, or two tasks actually. So this subtask creates output that will be used by input for subtask 3, that's that queue, and for subtask 4, that's this queue, and the same for the other ones. And subtask 3 receives input from both tasks from the previous stage. So in those queues, we have the network buffers, the infamous network buffers. They're there. We'll see some more details on them and on the connection as well. Oh, working? Yep. Probably most of you have encountered backpressure at some point. So let's have a look at this scenario. In that queue, we do have a lot of buffers assigned. We cannot keep up and consuming them as fast as we would get them from the previous operator. That will turn up as backpressure on here. But what was the problem? It doesn't only backpressure this single output here, because, well, we have the yellow boxes here that came from there. The way the network stack worked pre 1.5 is actually whenever you have this yellow network buffer here, that would need to go in here, but you don't have space, then it will be stuck in there and also block all the other connections, which is a problem that we addressed with 1.5 with a credit-based flow control. So let's see how that works. First, some terminology. So what we changed on the receiving side is that each input channel, actually the remote input channel, has a set of exclusive network buffers. Those are assigned only to that channel, while as there is some buffer pool for additional floating buffers that can be used by any of the channels, or there can be any split, like this one can have one floating buffer and this one two, or however. And then on the receiving side, we do account for the number of buffers that we have not sent yet, and this is called the backlog. So what this channel has now, it has two exclusive buffers that are sitting around. Actually, it doesn't matter which type of it's okay. So it's any buffers that are in there. We have two of them, and at first it is unannounced credit. So we call this, we have credit for two buffers to process. What we do now is that we announce this credit to the sender. So we tell the sender, OK, I have 2 buffers available. You can send me input for 2 buffers only. So the sender does account for this channel credit. It knows now it has 2, so it is able to send 2 buffers. It will start by sending 1 buffer, and along with this buffer, it will also send the backlog length. So at this point, when we remove that 1 buffer, we have 4 elements in the backlog. So we will send the buffer plus the backlog size, and the receiver will keep track of that as well. So the receiver now knows the sender has 4 buffers that it wants to send, but we didn't announce any more credits. So we gave it 2 already. We need to give it more for the sender to actually send more. So what the receiver does, it requests buffers from those floating buffers, from the floating buffer pool. So it asks for 4 buffers in this regard. It might get 4, it might get 3, it might get 1. We'll see in this example, we get all of them, so the remaining 3. And we have unannounced credit of 3. We did already announce this one, but we didn't announce the new ones. And then everything starts as it was before. We will announce the 3, and then it continues. The loop continues over and over again. So that's how credit-based flow control works. So let's see what it does, or what it improves. The thing is that we now have is what you saw here already. We don't have a full set. We always have capacity for something that is on the channel. So we never block the TCP connection. So whenever something is backpressured, we will not also backpressure another subtask on the same task manager. And that gives us better resource utilization, especially if you have data skew over different subtasks. Second thing is we do avoid overloading of slow receivers. So remember before, let's see whether I should jump back. So in here we have like 5 buffers that we couldn't keep up with. If now, for example, a checkpoint array would come in, it would need to be enqueued in here, and all those buffers would need to be processed before that checkpoint array actually gets to that task manager. And by having those credits, we do buffer less than before, because everything that is on the wire has been accounted for. That's what the credit does. So by using credit-based flow control, we also improved checkpoint alignment, and actually quite a lot. That was a simple example with a job that just has some shuffles and doesn't do much except for throughput. So we don't have any calculation in there, but we already see a difference in the checkpoint durations that was before using flow control at around 1.5 seconds, and now it's 500 milliseconds. Credit-based flow control comes with a small cost. So one thing is that we have those additional announce messages. Those flow backwards. Whoops. That's those announce messages that have been added. And the second thing is the backlog size messages, but these are at least piggybacked on the buffer messages, so they don't cost anything. It's only that additional backwards floating channel. And there's a potential round-trip latency that isn't involved. We will look at this a bit later. So let's look at the second thing that has improved. So that's a network stack as I presented it before, but it's not the whole truth. Let's add some more components to it. So it's actually sitting beneath. There's a netty server on the sender side and a netty client on the receiving side. It has multiple threads that will execute an event loop and feel responsible for some of the channels. All the subtasks will communicate with those servers and clients. Then the record has to actually get into the buffers at some point. So we do have a record from an emit operation or a collect that gets into the record writer eventually. There it will be serialized into, actually I'll have more details on the next slide. So it will get into the record writer that will then send it to the subtask that is responsible for that record. And on the other side, we have the same thing in reverse. We have a record reader that gives the next operator input. So let's have a look at the record writer. So we will actually look at the stream record writer for stream processing, because we did want to improve on latency, and this is where it counts. So we do have a record. That stream record writer will serialize it into an intermediate on-heap byte array. And from that byte array, it will copy bytes into a buffer in the channel. It will do so, like, you can copy as many bytes as they're available. And if the buffer is full, then we notify the NetT server, there's a buffer, please take it and send it out. And it will do so eventually. So whenever this event loop has time for that. And then we don't have a buffer anymore, so we will ask the buffer pool for a new one. And we'll eventually get one and go back to where we were before. We will continue writing from the rest of the record. If a record fits into, if a record fits into a buffer and doesn't fill it up, then we'll actually wait for the next record to add more data to it. And this is what we look at now. So we did write something into a buffer, and we're waiting for the next record to come in to fill that buffer. The problem with this is, well, we cannot wait indefinitely. A next record might come or might not come, but we want to have a low latency after all. So that's where the output flusher comes in. That's a thread that is spawned by the stream record writer and makes sure that the buffer is at most a configured time in that queue, and then it's sent out. It's actually not sent out, but NetT is notified and then it's been taken out. So that output flusher, by default, is called every 100 milliseconds. It will call flush on this channel. Then channel will notify the NetT server. And the same thing as with the full buffer will take place. The NetT server will eventually read the data. It will update the reader index in that buffer. That's a bit new. I will not take the whole buffer. I will only take the bytes that have been written. And this partially filled buffer will remain. It will stay in that queue because we want to continue writing to it. That was one of the changes that we did to improve latency and reduce on synchronization, because that flush kind of collides with the normal writing of the record writer. So in this component, we do need to synchronize. That's a different thread than the record writer thread itself. And we did see some overhead when we have lots of channels. And this is how we actually do it. We don't just have a buffer anymore that will be sent around, but we do have a producer, that's the buffer builder, and we do have a consumer. This will be read by NetT, and they exchange information partially. So the buffer builder you can append data to, then at some point you can commit and update a write position that is volatile, because this is in one thread, the record writer thread, while as the buffer consumer is in the NetT thread. And then the buffer consumer has a read position. This is the only one that reads from the record. And NetT can call a build function that will give us a read-only slice of the original buffer. And once it's full, it will be flushed as usual. And if it's not full, we will keep it however partially filled it is, and the next record will fill the rest. Let's have a look at some throughput. So this buffer timeout is actually a trade-off. Like, we did introduce those buffers in the first place to not call into the network stack for every record. Imagine you only send longs around, or maybe integers, then having a system call for every 4 bytes, that's quite too much. So you will reduce throughput immensely. So we do put those into buffers and then flush them, but you can flush them immediately. This is this side. The buffer timeout of 0 means you always flush with each record. You will get a throughput with Flink 1.4 that is, well, too low to see. With 1.5, you see the improvements already. So we did improve a lot on the latency throughput trade-off of the buffer timeout. So the default before and now is also 100 milliseconds, but you should be able to easily get down to single-digit without losing too much throughput. Let's have a quick look at the different connection types. First of all, every unchained connections, because chain connections don't go through the network stack, require serialization. So we always serialize a record into bytes, and then the next operator deserializes them. Secondly, we always assemble records into buffers. That is done for either remote connections or local connections. And what I showed before is true for all connections as well. We always forward the buffer when it's full or when the buffer timeout has hit. Now there's a difference between the remote connection and the local connection. The remote connection itself sends data over multiplex TCP connections. This is what you've seen before. And as soon as a buffer is on the wire, it can be reused. So this allows for a credit-based flow control to, this enables credit-based flow control and allows to control the amount of buffer data. While as in a local connection, you do have kind of a direct connection. Local connection is one task on a task manager and another task on the same task manager. Those communicate through channels as well. But whenever the sender sends a buffer, the receiver will use the same instance of the buffer. So if you cannot keep up, that instance will call backpressure in the sender as well. So those will be shared. And there you don't need buffer control. So credit-based flow control only applies to remote input channels, but this is the only part where it's actually needed. So let's look a bit more into tuning options, some of the knobs that we have for configuring the network stack for different use cases. So first of all, this credit-based flow control is new since Flink 1.5. We were a bit conservative on not replacing the old way. You can actually decide on whether you want to use credit-based flow control or not. We do see improvements, but there might be use cases that degrade. So the default is that we enable the credit-based flow control, but you can always turn it off if you see troubles. Then you can configure the number of exclusive buffers, so that's the buffers per channel, and the number of floating buffers. And tuning those two, like by default, we set 2 exclusive buffers per channel and 8 floating buffers. Reasoning was that whenever we're working on one buffer, we have another buffer available that is being used by Netty to put data in. Now it's back? Okay. So it is kind of crucial to configure those two things correctly, especially the exclusive buffers, because imagine this scenario when you start up. You have 2 exclusive buffers on the receiver. You did announce that, and you have the sender that immediately got a lot of data for whatever reason. So we have 5 buffers queued up, but we only have a channel credit of 2. So we can only send 2 of them. And we do piggyback the backlog size with the first buffer that is sent over, but we cannot send more until this one has gotten new buffers from the local buffer pool. So the number of exclusive buffers, those 2, need to be enough to cover this whole round trip time. So while you send the first buffer, you get it here, then you can ask for more buffers. And the second one is being sent. If you want to saturate the network, then this must match the throughput. So basically, the number of exclusive buffers times the segment size, this is the number of bytes that those exclusive buffers cover, should be the traffic that you can transfer during a full round trip. If you set the number of exclusive buffers too high, there's also a downside, because you're buffering more data. First of all, you're using more network buffers, so you need more memory in the network stack. And then inside, like the receiver, but also the sender, you do have more memory that you require. And the checkpoint alignment might take longer. If you set it too low, then you might have some periods of inactivity because you're waiting for this credit announcement to come back. So potentially you might need to tune those knobs, but I think the defaults are a sane start. Second thing you can configure is the buffer timeout. I said this before. It actually affects every unchained connection. So in this example, we do have a shuffle here, another shuffle there, and only some forwards in this field. So this is unchained, only local, same task manager, but it's still there. We do use the buffers, and therefore buffer timeout accounts as well. So if you aim for latency, for low latency, then the upper bound is the buffer timeout 1, 2, 3 times, if you count the latency between the source and sink. And we did see the trade-off in the chart before. What you can also tune inside the network stack is usually not necessary, is the number of threads that Netty uses. The default is the number of slots, each for the server and the receiver. There might be cases where those threads are the bottleneck. It shouldn't be. They should easily handle like thousands of channels as well. But if some additional computation like encryption over the channels comes into play, then you might need to look at whether it's a bottleneck or not. Also, on the other side, what I saw in benchmarks as well, if you have too many threads, they can also reduce the throughput. So apparently there's some downside in Netty as well. The only thing to figure it out, do your own benchmarks, because that's highly job dependent. In one job it works that way, another job totally different. So do benchmarks, then you'll see. Then what you can also use, starting with Flink 1.6. Again, actually, you can configure the Netty transport type to use either Java Neo or if you're on Linux, then the EPOL. And EPOL might reduce the overhead that the channel polling has between the Java and user space and the kernel and system space. There should be no downside to it. It's by default set to Neo. There's a Jira ticket open to switch this to auto, which will try EPOL first and then fall back to Neo. I would actually ask you to do some experiments with it. Try it out, try EPOL out, and leave your comments on that Jira ticket, because those will be highly valuable. If we cover more use cases, then we can actually decide on whether it's useful or whether there is a downside. Who knows? So do your benchmarks there as well. So I quickly cover some metrics that we have for the network stack. So they're the usual suspects. In the web UI, as well as through the REST API, we have the backpressure monitor that probably most of you have seen before. Then we also expose metrics for the inside of the network stack. And those are some of them. Like we have queue lengths of both input and output channels. We do expose a number of records that have been received, as well as the number of records that have been sent. And the same for bytes. Actually, that's numbytes out, local or remote, but numbytes in is separate for local channels and remote channels. And starting 153 and 161, which isn't out yet, we also expose the number of buffers that have been sent out. That's basically all of those. Well, the input queue lengths and output queue lengths can be seen as an indicator for backpressure as well. And the other two are for debugging the low latency changes or whether you use the network at its full capacity. Because we do send partial buffers now, well, we always did, you might end up with only small portions being sent anyway. Because if you, in the extreme case, set a buffer timeout of 0 milliseconds, you'll always flush with every record. You should see the overhead in the number of bytes per buffer. But even if you set it to something like 10 milliseconds, you could get low rates there as well. But that's the trade-off between throughput and latency. There's one metric that I want to talk about a bit more in detail, because that has actually troubled us a bit. I don't know how many of you have actually used the latency markers that we exposed before. Is there anyone? Is that just for debugging or in runtime, like in a production job as well? Anyone in production job? Okay, that is actually meant to be a debugging metric and has some overhead. But let's first explain what it does. So whenever you enable the latency tracking, and it's enabled by default, the sources will periodically emit a latency marker, by default every 2 seconds, and this latency marker contains a timestamp. Now those latency markers flow through the whole job. They will issue behind records. They will not skip them. They will, however, not be put into windows. They will kind of bypass the operators, but they never overtake records. So they actually resemble the latency that your records have as well, without the windowing over it. Like when you put a record into a window and let this window open for a second, then there's a second latency by that window. So that latency markers are there for looking at the latency of the network stack itself. And once they're received on one channel, they will be put onto a random output channel. So we don't flush the whole network with latency markers. We do walk some random paths, and eventually, if your job runs long, you will have all paths covered. And what we do at each operator when we receive a latency marker, we do collect a histogram of those latency metrics. So the time, like the current time between the difference between the current time and the starting time of that latency marker. And those will be collected in the histogram of window size 128 elements. You can easily, okay, and let's say first that metric is actually exposed as it's a latency between source ID something, source subtask index something, and then my operator, operator ID, operator subtask. So you can do the math on how many latency metrics there are. If you have 10 operators, one of them being the source, you have a parallelism of 100, you have 9 non-sources, times 100, that's the total number of subtasks, times 100 sources, because that's combining every source and every operator. So you have 90,000 histograms. Those histograms, first of all, consume memory. You have this window size here. There, internally, it could actually go to 256, and shortly even a bit bigger, especially if you request the metric. But those metrics kind of flush the metric system. So if you have 90,000 metrics here, that might easily overwhelm the whole metrics reporting. So it is actually recommended to turn it off. We're thinking of, for production, we are thinking about changing this default to turn it off. We'll see how that goes. But you can always configure this yourself in the job, not as a configuration in Flink YAML, but in your job, you get the execution config and set latency tracking to 0, or something less than 0. That disables them. And if you ever need them, then you can enable them for debugging. All right. So, common anti-pattern. I think, what is it? Several presentations have already shown this particular case in the past. Whenever you do have a keyby, for example, in here, you do keyby location, then you do a map or whatever, and then you have a next operator that also wants to access keyed state. You need to keyby again, because that keyby is not preserved. Well, I think most of you are aware that this is some overhead that you can circumvent with a, let's say, dangerous reinterpret cast, if you know what you're doing. Flink cannot optimize this case itself, because for this user-defined function, we don't know what it does. And whenever we do a keyby, we don't extract the key and keep it separate to the record. So whenever we do need to get the key again, we will actually extract it from the original record. And since the user can change that record here, we cannot use the same function. But if you don't change it, then you can reinterpret that data stream here into a keyed stream, and then those operators can, for example, be chained into one, because if you have multiple keybars, multiple shuffles, those will not be chained. And in this talk, we will look at what is happening in the network stack if you do this. And that's of particular importance because of the credit-based flow control and low latency changes. So we'll look at the second keybar, the unnecessary one. So first one is necessary. This one can be replaced by reinterpret cast. So this is what will happen in that second one. Since we are already keyed and we didn't change the element, the output of, let's go back, the output of the enrichment here towards the window will actually only use one output channel, and that's a local channel. I will only forward data to myself, but since that was a shuffle, I will add queues for all the potential other output channels as well. Same goes for the receiver. The receiver will have input channels for each of the potential inputs, but only one of them will be used because we're already keyed. And each of those input channels will have exclusive buffers assigned. So that increases memory usage a lot. Like, instead of using just 2 exclusive buffers for this whole communication, if you didn't chain it, we're using, in this example, 5 times 2. So we did increase memory usage a lot in there. That's one problem. But it's not only a problem on the receiving side, it's actually also a problem on the sender. Because the sender has a shared buffer pool, so we don't assign exclusive buffers on the sender side, but we have a shared pool. And this pool, like any of the channels, can pull from this queue, from this pool. But those empty channels will never pull from this one. So we now have a pool that's actually the size of the pool. It's the number of channels times 2. We actually use the same configuration as for the exclusive buffers, plus some added buffers. So we will have a single channel using 5 times 2, so 18 buffers. Whereas if we only had this one channel, we would be using 1 channel times 2, so only 10. So we do have more data here. And that becomes a problem for checkpointing. If we have more data that is buffered between 2 operators, whenever a checkpoint barrier comes in on this side, all those will need to be processed. So that's the second problem of that. And there's a third one. If anything would actually use one of those empty channels, and since latency markers go random paths, they are free to use those channels as well. This is one example, if you ever had a broadcast, but that's uncommon in this regard. So if you ever have this, like latency markers, you would have some buffers sitting around here as well. Now recall that we did those low latency changes. So whenever we have a buffer that is partially filled, we will keep it here. We will read the data that has been occupied, send it through NetI, done, but the buffer will keep here, linger around in here as well. Now this wouldn't be a problem. Actually, you could see this as an advantage, because that buffer is here and not here. So we reduce the number of extra buffers that are put on here, not to the same amount that we would have for one output channel, but we would reduce it. But actually, that's an additional problem, because the output buffer needs to synchronize between the flush and the record writer. So we can optimize the part where we have an empty channel, but not the part where there's something in the channel. So that's an additional overhead. So whenever possible, reinterpret the stream. All right. So now we looked at the network stack, and I think, or I hope at least you got a good overview. Let's look at the things that are up next. What could be there in the next versions? So one thing that's already a pull request by Alibaba, actually, is that if we ever broadcast a record, we will, at the moment, serialize this record once per output channel. So that's some overhead that is unneeded. We consider it as it once and then simply copy the bytes there. But then there's a second thing. Inside the record writer, we do have intermediate buffers that we serialize this into. But only ever one is used at the same time. So by having that optimization, we also remove the second intermediate buffer. And this considerably reduces the memory footprint on heap in the record writer. We're also trying to optimize the overhead that is done for SSL encryption and decryption in the channels. So one way that was recommended on Netty is to actually not rely on the JDK and the JVM's SSL engine, but use a natively running OpenSSL. And that might use optimized CPU instruction sets that modern CPUs expose. So that potentially reduces overhead. What we still need to do is some benchmarks. There's an initial pull request, but we need verification. What else is there? We did already do some improvements for the latency cases. There's one coming up as well. And this will further reduce the synchronization overhead by moving the output flash, by not having the output flash as a separate thread, but actually letting Netty do the work for us. And those are some initial benchmarks in here. So the average throughput is increased by doing that as well. The max is actually the same, but what we do reduce is the minimum throughput, because the current solution does have problems with garbage collection. By notifying Netty that there might be data to be consumed, we put some pressure on some intermediate objects. So those can be reduced with that change. And that will actually be it, apparently. Thank you.
Thank you, Nico. So I think we have time for just one or two questions. So does anyone have any questions? Anything you wanted to know about the network stack? There we go.
Is there any way you can provide auto-tuning of the exclusive buffer, which you said at the round trip time times throughput? Mm-hmm. Is there any way that Flink can support auto-tuning?
I'd say the question was whether we can auto-tune the exclusive buffers based on like previous.
Yeah, for example, round trip time can be a dynamic thing. If network deteriorate, the round trip time may make it worse. So if that auto-tuning makes sense.
Yeah, you could actually do so. Like we do have this global buffer pool that might have some extra buffers. So you could communicate with this and say, okay, I do have some buffers left that could be put into this exclusive buffers, into those exclusive buffers. The downside is that you then actually buffer more. So you will make the checkpoint alignment worse. So that might be like there's a trade-off in there as well. So someone might opt for having a fixed number of exclusive buffers for exactly that, improving the checkpoint alignment, and then he doesn't want auto-tuning.
Do each of the task managers maintain a connection to every other task manager, or are those brought up as needed for operators?
Different tasks. So let's see whether I can jump back to the job that I have there. So we will have one TCP connection here, one here, and well, this is only local. So for every task, like this could be a chain of operators. There's no network communication, but in here we have one TCP channel.
And in one direction, right? So if I have, say, in that first box, I have a parallelization of 50, and then I have 100, it's 50 guys, it's 50 talking to 100, right?
Yes, because the shuffle will need to send to all of the outputs. I mean, I can imagine that we could use fewer channels, actually, since the credit-based flow control changes. Before that, this blocking problem might actually, like if you have this one channel blocking all the others, if you have it in here, then it would also affect in here if you would use the same TCP channel. Since we don't have that anymore, we could actually think of using only a single channel. But using more channels might also give you more throughput. So
All right, I think we're out of time. Thank you, Nico, and thank you for the questions.
Thank you.